Okay. Hi, everyone, and welcome to another session of this course. Today, we're going to continue what we started in the previous session with writing smart contracts in Solidity. So let me share my screen, and then we can go on. Okay, so if you open the Remix IDE, you will already see a bunch of contracts that are here. And you can use this as maybe the starting point of your contract writing. And this is the contract that we wrote last time, where we basically had this king title that anyone could claim. Now, today I'm going to go a bit further on these things, and I'm going to show you some examples of contracts that basically demonstrate how you can do things in a better and more systematic way in Ethereum than you could do in Bitcoin. And I will hopefully also show you some of the pitfalls and some of the, well, really weird vulnerabilities that can happen when you use these kinds of contracts. Okay, so let me just create a new file here. I'm going to call this B. And again, as before, we have to start by saying what version of Solidity we're going to use. And then we're going to have a contract. We can give it a name. Okay. So which contract should we start with? Let's actually start with a very simple contract. And let's say that I want to have a bunch of money in my contract, and I want to have two people, Alice and Bob, who can interact with this contract, and each one of them can take the money out. Okay. So this is what I want. I want to have an address for Alice and an address for Bob. And actually, let's hard code these addresses. So let's say this first account here is Alice. And let's say my second account here is Bob. Okay. I could write this in the constructor, or I could just write it like that. And yeah, let's say I have a function called deposit. And what this function does is that it's public, anyone can call it, and it's payable, so anyone can pay it. And yeah, it just doesn't do anything, it just accepts the payments, right? And let's say I have a function called withdraw, and this is also public, and anyone can call it. Now, what I want to say is that I want to say whoever calls withdraw gets to get all the money that this contract has. But I don't know how to reference that. So generally, I will just Google this. So you can just Google how to get contract balance in Solidity. That's like the first thing that you find here. Okay. So you see that you can just say address this.balance. And this gives you the balance of the current contract. So in your contract, whenever you write this, it will actually give you an address that points to the current contract. So what I can do here is that I can say, well, take whoever called this function, so message sender, and transfer to them, well, what do I want to transfer? I want to transfer the balance of the current contract. So I just take the address of the current contract and I say this.balance. Okay. Now, the problem that we have here is that, as I showed you in this previous example, so we have two different data types. One is just address, where you can save an address, and one is address payable, where you can save an address that you are willing to pay money to. Okay. And you cannot just convert between these things easily. So instead, what I have to do here is that I can say address payable receiver, and I can say that this is the message sender, but I have to be very specific that I want to make this payable. And this is something that Solidity enforces so that it makes sure you don't mistakenly send money to somewhere you don't want to send. And then I can say the receiver gets the whole balance of this contract. Now, this contract is quite silly in its current form, but let's actually put it on the blockchain and just work with it a little bit. So I can do deploy. So this is my contract. And I can use one of the accounts. For example, I can use, let's say this one, to deposit some value. And let's say I want to deposit 2 Ether. So I just set the value to 2 Ether and I call deposits. And as you see, this was successful and my balance decreased by almost 2 Ether. So 2 Ether was sent here and I also had to pay for the gas. Okay. Now, anyone else can call the withdraw function. So let's say I use this last account here and I call the withdraw function. And as you see, again, this was successful and my account got almost 2 Ether. So it got 2 Ether, but it also had to pay for the gas of the function call. So it's a little bit less than 2 Ether that is added to the balance overall. And you can see the details here as well. Okay. Now, this is, of course, not a great thing. And of course, what I want here is that I want to do some access control to make sure that not anyone can just call withdraw. So I can just say here that I require the sender of the message or the person who's calling this function to be Alice, or I'm not sure how I write or here. I think it's like this, or for it to be Bob. Okay. Now, if I have this new contract and let's say again, I deploy it. Now, still anyone can deposit. So I can use this account that wasn't either Alice or Bob, and I can deposit, let's say 3 Ether. Okay. But now if I want to withdraw, let's say with this account, I call withdraw and it fails because it wasn't either Alice or Bob that we had hard-coded. So now I can use Alice's account. So remember this DC4 was Alice. And I can withdraw using this one, and this worked. And as you see, the balance also increased. Again, we had to pay some gas, so we didn't get exactly 3 Ether, but that's fine. Okay. So now consider a contract like this. This is actually a good starting point for me to tell you about some of the weird things that can happen on the blockchain when you have contracts. So suppose that I have deployed this contract. So again, I've deployed this with some account. I don't care which account this was. And let's say that I've deposited 10 Ether in there. Okay, so my contract now has 10 Ether. Now what's the problem? The problem is that both Alice and Bob can call this withdraw function and they can get the 10 Ether, right? But the thing that we said last time is that whenever you want to call a function, what you're actually doing is that you're actually creating a transaction and publishing that transaction on the network, and then a miner would mine it. And as I said before, the problem here is that we are not really running this on a real blockchain, we are just running it in a virtual machine. So a lot of these attacks that I tell you about are not really detectable if you just use this remix ID and write everything here. But you have to constantly think about what happens on the real blockchain. Okay, so there are two questions here. So the first question is that the account balances are back to 100 again. Yes, that's because, again, we're just using a virtual machine here. This is not the real blockchain. And the other question is, how is the deposit function working without any content? So what is this deposit function? Well, it's just a function that anyone can call. It's public, and it's also payable. And payable means that when I call this function, I can pay some money to it. And when I do that, that money actually belongs to the contract, not just to that function, right? So this deposit function is working because I don't have to do anything. It's like, I don't want to really execute any code when a deposit happens. I just want to make sure that I can get the deposit. So I can just have this dummy function here that is payable, so anyone can pay it, but it doesn't actually do anything other than getting the payment. Okay. So another question is, so in the king of ETH example, we first pay the contract and then the contract pays for the king? Yes. So here, if you look at this function that we had, which was called become king, this was also a payable function. So anyone who called this function could also pay some amount, right? And this amount was accessible by msg.value, as we said before. And what we would do here is that we would first pay this amount that we just received to the previous king, and then we would change the king. Okay. Yeah, another question is about payable functions and what is the ownership of the money that you give them. Generally, when you consider what's happening on the blockchain, we have, as I said before, we have different types of accounts. So we have externally owned accounts, and we also have contract accounts. And each one of these accounts can have a balance on our blockchain. So only accounts can have money. So when I call a payable function and I pay it some money, that money will become the property of the account, which is actually the contract. So even if I pay the deposit function, the withdraw function can still access those funds. Okay, so the ownership is with the contract. Okay, now coming back here, the problem that I want you to see is that I have this contract right now and I've paid it a bunch of money, and I have this code here. So both Alice and Bob can call the withdraw function and try to get the 10 ETH that is in the contract. But what happens if they are in a competition? What happens if both of them want to do this? So Alice creates one transaction that contains a call to this withdraw function, and Bob also creates another transaction that contains a call to the same withdraw function. And they both put their transactions on the network, and the gossip protocol in the network sends the transactions to everyone else. Now, a miner gets to choose which transactions he wants to put into his block. So let's say I am the miner who is mining the next block. I will see two transactions. One is from Alice calling the withdraw function, and one is from Bob calling the withdraw function. Now I can choose which one I want to include into my block. And I can even choose to include both of them in my block. But the way this function is written right now, actually the order really matters. So if in my block, so let's say in the mind block, I can have several cases. I can just have Alice's withdrawal, but not have Bob's. Or another case that I can have is that I can just have Bob's call to this withdraw function, but not Alice's. And these two cases are trivial, what happens. So in this case, actually, Alice gets the money. In this case, Bob gets the money. But there are also other cases. So I can put both of them. So I can first put Bob's withdrawal in my block as a miner, and then put Alice's. So if this happens, this effectively means that the function call by Bob is going to be executed first. So this will be executed first, and Bob gets all the money. And then the function call by Alice will be executed. And when that happens, again, we go through this function and it works. But the problem is that the balance of this contract is already zero because Bob has already taken all the money. So as you see, the miner can just put Bob's withdrawal before Alice's withdrawal, and that makes all the difference. That means that Bob gets all the money. And of course, we can do the opposite. As a miner, we can put Alice's withdrawal first, and then Alice gets all the money and Bob gets nothing. So this is an example for you to see how miners really have a lot of power here. And whenever you write a smart contract, you have to think about what the miners can do. And you have to make sure that you write your contract in a way that miners can have as little influence as possible on what happens and who gets the money. Okay. But we can even actually, let me talk a little bit more about this. So suppose that you have a situation like this. Suppose that you have a contract in which the order of these function calls matter, and let's say you're Alice. You want to make sure that your function call comes before Bob's function call. Okay. So how can you ensure that? One way you can ensure that is by just bribing the miners. So how can you bribe the miners? As I said before, you can decide how much you pay in transaction fees. More specifically, you can decide what is the amount of money that you're willing to pay for each unit of gas. Now, we can't do this in this virtual machine, but on the real blockchain, you can do it. So what Alice can do in order to make sure that her transaction gets on chain, and probably gets on chain before Bob's transaction, is that she can just pay much more in gas fees. Yes. But now another problem is that, well, in this particular case, this will not help, right? So if I have a situation like this, the miner will get the same amount of transaction fee no matter which ordering he chooses, right? So if I have a withdrawal by Bob and a withdrawal by Alice, and even if Bob is paying much less in transaction fees, in gas fees, at the end of the day, a miner who puts both of these into the block is going to get the transaction fees of both transactions, both Alice's withdrawal and Bob's withdrawal. So in practice, Alice can actually pay more, and that would really make the miners put her transaction first, but there is no guarantee. Now, one thing we can do is that we can actually try to bribe the miners in a more direct manner. How can I do that? Well, suppose I'm Alice, and suppose that my account has a very small balance. So let's say Alice's balance is, for example, let's say a very small number. Okay, I'm going to give you random numbers here, but anyway, so let's say I have 2 ethers. And let's say that I want to bribe the miner 5 ethers to put my transaction before Bob's transaction. So as Alice, what I can do is that I create two transactions or two function calls. And this is the way it works. My first transaction is just a call to this withdraw. Okay. And then my second transaction just says send 5. I don't know what's wrong here. My second transaction just says something is wrong with me. Okay, my second transaction just says send 5 Ether to some miner. Okay, and what I can do here is that I can just put the address of one of the big mining pools, for example, or someone that I'm sure will be the miner for the next block. And the way I can do it is that I can just take like the top 4 or 5 miners and I can create transactions that pays each one of them, right? Now, here's what happens from the point of view of the miner, if the miner is really smart and can see what's happening. So the miner would see that there is a call to withdraw from Alice and there is a call to withdraw from Bob, right? But he sees that if he puts Alice's call first and makes sure that Alice gets the money, then there is this other transaction that is already propagated on chain in which Alice is going to send 5 Ether to the miner, right? But Alice will have this 5 Ether only if her call to withdraw was successful and came before Bob's call to withdraw. So the miner gets these 5 coins only if he puts Alice's call to withdraw before Bob's call. So now we are basically bribing the miner. And a rational miner, a miner who wants to maximize their own payoff, would then put the transaction by Alice first. And you see, so this is a very complicated game theoretic behavior where someone is basically bribing the miners to do some things. And all of these things that are happening outside of our contract. And that's very undesirable because generally what we wanted to do was that we wanted to have a contract that basically tells us what's going to happen with the money. And we didn't want to have these side games. But because this contract is written in such a terrible way, it actually allows miners to have this kind of say over what's going on. And then it allows participants to bribe the miners. Okay. So let me just go to the questions. So one question here is that, can't we just require that the balance is greater than 0? That's a nice idea. Okay, so I can say require. And here I can say that I want the balance of this contract to be greater than 0. So I want to say if this contract doesn't own any money, any call to the withdraw function will just abort here. But again, this will not really change it that much, right? Because again, from the point of view of the miner, yes, the second transaction here is going to use less gas because it fails in this require. So now it makes sense to put the transaction that is paying more per unit of gas first. But this is a very small change, right? So anyway, you're paying very little gas for this whole withdrawal function. This is, on the other hand, a much more well-designed attack where the miner actually gets a lot of money for doing this. So it's likelier, I would say, that the miner gets incentivized by this kind of attack than by just making sure that he makes a little bit more in gas fees. Okay. So another question here is that, are transactions made simultaneously for all transactions in the block, or are they made sequentially? So we don't have any kind of parallelism here. Everything is going to be sequential. as a miner, you get to decide which transactions you include in your block, and you get to also decide the order of the transactions. So the miners basically put the transactions in order, and then all the transactions in the block will be run sequentially. Okay. And this also, I think, answers the next question, which is, will we have a race condition? Technically, no, because again, the miners decide the order. But as we saw here, this can be considered a race condition, where from the point of view of both Alice and Bob, what they want to do is that they want to make sure their call goes first. But again, from the point of view of everyone else, all the nodes on the network, what they see is just a block that is mined by a miner. And this block tells them the order of the transaction. So they just run it in that same order. Okay. So the next question is, let's say if Alice knows how much the balance of this transaction has, then in transaction 2, she pays an amount that is more than the sum of her own balance and the contract. Okay, of this transaction. Okay, eventually she can bribe the miner without paying extra money. Well, I mean, the miner is seeing what's happening on the blockchain, right? So the miner sees Alice's balance and the miner sees the balance of this contract. So if she's actually not paying the money, I don't see how that can be considered a bribe. Okay, yeah, I'm not really sure I understand this question. Okay, but let me just go back here. So we have these two addresses, Alice and Bob. But another thing that we can do is that we can maybe have another function where Alice and Bob sign up in this contract instead of just having this address hard-coded here. And suppose that we have that. So if that happens, as I said before, an address can basically point to any account on the blockchain. And since the accounts can also be contracts, what that means is that Alice can be a contract. You can have a situation where this address here is just the address of a contract. And if that happens, then that opens the door to all sorts of more complicated attacks. Okay? So let's say that I have some contract. Let's call this Alice's contract. Okay? And let's say that the address that I have here, I'm not going to do this because I need to be able to access these addresses in my virtual machine here. But let's say the address that I have here actually points to this contract. Okay. So what that means is that I have this other contract, and this contract can call the withdraw function in my original contract. Okay. So let's say I have a function here. Let's call it f for now. And let's say that it's public. Okay, so how can I call the function, the withdraw function of a different contract in my current contract? Well, I basically need the address of this other contract. Okay, so I have already deployed this other contract. So this is the other contract, and I can just copy its address. Okay, but before doing that, let me actually remove this. Let's, just for the sake of this example, let's say that I have a function called setAlice, and let's say it's public. Again, this is not a great idea, but I'm just doing it as an example. That takes some address A, and it sets Alice to A. Okay. So let's say I have this. I deploy this contract. and I deposit some money. So let's say I pay 5 Ether to this contract. So this is my first contract. Now I have this other contract, which I'm calling it Alice's contract. And I want this contract to be able to call the withdraw function in this one. So generally, when a contract wants to call another contract on the blockchain, this has to be done by address. So what I can do here is that I can say this new contract that I have takes the address of the original contract. Let's just call it, let's call it contract. I don't know what's wrong with my, okay. So let's say I have a function like this, and let's say that the address that I'm passing here is basically a pointer to my previous contract. Now, what can I do here? Well, I can use this, my contract, as a type, because basically, as I said before, we think about these contracts kind of similarly to how we think about classes in the Java programming language. So I can have some instance of my contract, which I call C. And this can basically be the instance that is at that particular address. Okay. And then I can say I want to call C.withdraw. Okay. So this is how you can have one of your contracts call another one of your contracts. So I note that I have to first deploy my first contract so that I can have the address of it. And then I deploy my second contract, and I have to give my second contract the address of my first contract. Okay. So let's say I deploy my second contract now. Okay, what's happened here? Okay, not great. Let's try this again. So you deploy, it deployed only my contract, it didn't deploy Alice's contract. Okay. Yeah, the problem is that I'm not really sure how to deploy this second contract in this remix framework. Oh, okay, yeah, thanks. Yeah, I usually don't work with remix, so that's the problem. Okay, so I first deploy my first contract. I can choose which one here. Great, I deployed this one. And now I deploy the second contract. Okay, and as you see, I have both of these contracts. So what I can do is that I can first copy the address of the second contract and pass it to setAlice function in the first contract. Okay, now basically what I did is what I wanted here. So this Alice in my first contract is now actually not controlled by some real world entity, but is the address of this contract. Okay. And so now here's what happens. Suppose that I want to call withdraw. If I call, okay, actually, let me switch to a different account. And let's say that I first deposit maybe 10 Ether here. And then let's say that I call withdraw. This will fail because I'm neither Alice nor Bob. Okay. But actually, this contract is now Alice. This contract can now call this one. And it makes sense because the message sender will be this contract, which is Alice. And then this contract can basically get money from this. So if I just call this F function, I have to, of course, give it the address of the other contract. So I just copy the address of the other contract, put it here, and I call the F function. Okay, and it failed. Okay, I'm not sure what's going wrong here. Ooh. I hate the virtual machine. Okay, so actually, let's simplify things a little bit to make sure everything works. So let's do it like this. And let's say this address is public so that everyone can see it. And let's say that only Alice can get the money. So again, I'm going to deploy original contract first. And I can see who Alice is. So this is Alice. Now I'm going to deploy Alice's contract. And I'm going to copy its address and give it to set Alice here. Now I can ask who's Alice. Okay, Alice is now this other contract. And now what I can do here is that I can call the F function here using the address of this contract. Okay. And it's still failing. Okay, so maybe again I have a problem with this version of Solidity. So let me see. Call a different contract in Solidity. They changed things in version 0.5, so it is possible that I'm calling the contract in the wrong way. Okay. Store value. Okay, this doesn't seem to be a problem here. I don't think I need to use new. Okay, anyway, sorry about this because yeah, I haven't really coded with the new versions of Solidity and this is looking unexpected to me, but I'll fix this later on. But here's what I wanted to tell you. So suppose that I can fix this and I don't know what's wrong right now, but let's say that I fix this and then basically this contract can serve as the Alice in this other contract. So then the only way to call this withdraw function is through this second contract, because now the second contract is basically Alice. Okay. Oh, actually, maybe the problem is with the transfer here. Yeah, so I don't have a default behavior in this contract for what happens when someone transfers money. Okay, anyway, so now if I have a contract like this, and if this contract is the one that actually is taking part in the other contract, then I can do all sorts of crazy things in this contract. And I can, for example, again, bribe the miner in this contract. So what I can do here is that in this contract, I can say, okay, first withdraw from the previous contract and then pay a bribe to the miner, right? And again, the way I can do this is just like before. So if I have the address of the miner, I can just say pay a bribe to the miner here in the code of this contract. Okay. And another way that I can pay a bribe is that I can look into the blockchain, and generally the contracts have access to anything that is written on the blockchain. So as you see, for example, here, the contracts can check the balance of a particular account. And in this case, I'm checking the balance of myself of this contract. But I can also access other things. And so let me see if I can find a list. So I can just say Solidity block information, or okay, globally available variables. Okay, so what you can see here is that we can actually we can access a lot of things, a lot of information about the current block in our transaction. Okay, so I can write something like block hash and it will give me the hash of the current block. I can talk about base fee and so on. But what I'm really interested in is this one. So block.coinbase. And as you see, it says that block.coinbase gives me the current block miner's address. So this is what I can use for paying bribes. I can come here and I can just take this block.coinbase and I can say pay or transfer some amount here. Okay, I just put some number. Now, what does this mean? Well, if I call this function f, suppose that I'm the real Alice, the real world Alice, and I'm taking part in this contract, not using my real world identity, but using the identity of this other contract that I've written. Now, instead of directly calling the withdraw function in the original contract, what I can do is that I can call this f function in this auxiliary contract that I have here. And let's say that I had a case like before where either Alice or Bob could take the money out. So let's say that Bob is just trying to create a transaction where he withdraws this money. And as Alice, what I do is that I just create a transaction that calls this function f. Okay. Now, for this function f to work, since the balance of this contract is 0, it should be that the withdrawal here is successful. It should be that I withdraw before Bob has withdrawn, so that I have some money that I can then transfer here to the miner, right? So again, we are in a case where we are bribing the miner to put our transaction first, because this is a transaction that pays the miner, and I can pay whatever amount I want here, but it pays the miner only if this withdrawal actually gives some money to this contract. And now again, as an attack, what I can do is that I can put this contract on the chain, and then I can call the function. Now, this is a bit nicer than the previous attack because here I'm literally just referencing the miner. Whereas previously I had to guess who the miner of the next block is going to be and try to bribe them. Now the only thing that I can do is that I can just write block.coinbase, and that means the miner of the current block. And it will definitely pay the miner. So the miner will definitely now be incentivized to put the call to this function f before Bob's call to the function withdraw. Okay? Okay, looking at the questions here. So one question is this set Alice a well-defined constructor? Well, this is not really a constructor. I just defined it as a function. You could, of course, define it in the constructor. So you could have a constructor here, which basically sets Alice and Bob. So I could, for example, say that in my constructor, Alice becomes whoever put this contract on the chain. So it becomes the message sender. But this is not a constructor. This is just a normal function. Okay. And there is also another question, is there a built-in function to retrieve the miner's address? And yes, so there's block.coinbase. It's not exactly a function, but it gives you information about the current block. Okay. Nice. So this is an example where you see that miners have a lot of power. But I want to give you just one more example before this session is over of the power that the miners have. So let me just create another contract, and let's call this one puzzle. This is the very first contract that we saw before. So I can have a function that is called claim price. And let's say that it's payable, or no, let's say it's public. And basically the idea here was that I have a string X. I have to actually write it like this in the new versions. And what I do is that I take the hash of this string. And again, you can just Google this, like hash functions in Solidity. And so you have a bunch of different hash functions. You have, for example, SHA-256. So I can just take this one and put it here. And what I can do is that I can take the SHA-256 hash of this X. And if it is equal to some hard-coded value, so if it's equal to something, let's say, whatever, I get a compiler error because I wrote whatever there, but okay. If this is the case, I can say that pay all of my balance to the person who called this. So again, the same thing as before. So I will just say, take the person who is the sender of the current message, so whoever called this claim price, and send them all the money that the current contract is. Okay, actually, let me just put something like this here. I think we have a typecast error. Okay, we have to also change the type of X, but that's not a big deal for us for now. Okay. Yeah, so as you see here, we need a type called bytes and not just string. So we have to convert it to this type first. But I'm just going to continue with the example. Just know that you need a type conversion. So let me actually see if I can do it like this. Not compatible with types bytes 32. So let's just call it bytes 32. Okay, I don't care. Anyway, we have to also change the type of this one. But anyway, so making sure we do the typecasts. I really hate the new versions of Solidity. What does this contract do? What this contract does is that it says anyone who can give me some value of X such that the hash of this value is this predetermined amount that I have hard-coded here, will get all the money that belongs to this contract. Okay? Now, suppose that I deploy this contract on the blockchain, and suppose that I pay it a large amount. So let's say I paid this contract, for example, 10 Ether. So what I'm saying is that if you can find the right value of X that has the right hash, you can just create a transaction that calls claim price and gives me the right value for X, and then you will receive them. Now, this is another case where the miners can actually do some really weird attacks. And here's how. So let's say that I'm the miner of the current block. And let's say that I see a transaction by you that is claiming this price. So what I see is that someone is calling this function and they're giving a value of X. And because that value of X is correct, they're being paid this huge amount. So they're being paid, for example, 10 Ether. Now, as the miner, what I can do is that, again, because all the transactions are public, because this transaction is propagated over the network, I can just steal this value X, right? So I can create my own function call, my own transaction containing a function call to claim price that has that value X that I just stole from your function call. And since I'm the miner, I can decide to put my function call before yours. And basically using this attack, what would happen is that I am the one who gets all the money. So the miner can basically steal the solution from anyone else. And this is actually a very common attack. It's called the front-running attack. And it's very important that when you write contracts, you have to make sure that your contracts never are vulnerable to these kinds of attacks. So you have to make sure that it's impossible for the miners or generally for anyone else on the blockchain to just steal the parameters that someone is giving to your contract and claim that function call for themselves. Okay, so yeah, this is all for this session. I'll stay and answer questions, and then I will fix the type errors and the small things in these contracts and put them on Canvas. Okay, thank you, and I'll see you in the next session. Okay, so one question here is, what does this line mean? Okay, so the way I'm thinking about this is that I'm thinking of every contract as some sort of class in Java, right? So I can have different instances of this particular contract. And each instance of this contract will have some address, right? So to just make it a bit more obvious for you, what I can do here is that I can take my contract and I can deploy it, right? So when I deploy it, this is one instance of my contract and it's deployed to this particular address. But I can deploy it again and again. And this just gives me more instances of the same contract. Okay, so these are all the same contract. They have the exact same code, but they have different addresses. So it's very similar to different instances of a class in Java. Now, in this contract here, what I'm saying is that I'm saying I want the instance of the original contract. So this is the type, my contract. And I want the instance that is at this particular address. And then I want to withdraw from that instance. So when we talk about a contract, we have to actually kind of be more specific and say if we are talking about this particular code, which works like a class, or are we talking about a particular instance or deployment of the contract? And here I want to talk about a particular instance that is at a given address. Okay, so another question is, what was the name of the attack for the hash part? Okay, so the attack is called the front-running attack. And again, basically the idea is that I look at a transaction that is already published on the network and I steal some information from that transaction. For example, in this case, I steal the value of X, and using that, I create my own transaction. But then I try to somehow make sure that my transaction, even though it was created later, happens earlier than the original transaction on the blockchain. Okay. So there are some questions about homework 2. I will open the resubmissions hopefully today, as soon as all the grading is over. There are a few submissions that are not yet graded for homework 2. So another question here is that these two contracts are in different transactions. How can the compiler know which my contract in the network we are referring to? Okay, so the compiler doesn't actually know. So the way it works on a low level is that the compiler just knows that I'm talking about a contract at this particular address. And the other thing that the compiler knows is that I'm just calling a function called withdraw that is at the contract at that particular address. And this can be compiled. So in this case, it helps the compiler that I have put the code of both of these contracts in the same file. So if I had some parameters here in the withdraw function, the compiler could also know what kind of what kind of typecasts it has to do. But generally, we don't need this information, right? So in order to call the withdraw function, I don't need to know that this C is of type my contracts. The only thing that I need to know is that there is a contract at a particular address on the blockchain that contains a function that is called withdraw. And if I just know that, then I can call the withdraw function. So another question is there a standard solution for front-running attack, or does it really depend on the behavior of the function? I don't know of a standardized solution. Generally, you can create vulnerability to this kind of attack in many different ways. So this was just an example, but you can do whatever you like in your contracts, and it's possible to create this kind of vulnerability in a million different ways. So yeah, the only thing I can say is that whenever you write a contract, try to reason about this and try to make sure that you're not vulnerable to this kind of front-running attack. Okay. So another question is, so I can just write contract address.withdraw? Yes. Well, I don't know if the Solidity language allows you to do that, but actually on the blockchain, what you can do is that you can just create a transaction that says, I want to withdraw from this particular contract address. Or I want to call this particular function of this particular contract. That is, well, I have to just give the contract address, the name of the function that I want to call, and the parameters that I want to pass to that function. So another question here is, when you create a new instance of the my contract class, that instance doesn't inherit initial coins, right? Yes. So each instance is its own account on the blockchain. So each one of these instances has its own balance, and the coins between them will not be the same. So it might be the case that I have deposited a lot of money in the my contract at this particular address, but nothing at this other address. And they're basically independent of each other. The only similarity is that they have the same code, right? But they're not the same. They're different instances. They have their own money. Okay, any other questions? So there is a question that says, so when you call withdraw, nothing should happen to the my contract transaction, right? I'm not sure what you mean by the my contract transaction. So, oh, okay. So you're misunderstanding this. What I'm doing here is not creating a new instance of my contract. So my contract it already exists at this particular address. And what I'm just saying is that let C be a variable that basically points to the my contract instance at this address. So when I'm calling F, I don't want to create a new instance of my contract. I just want to access an instance of my contract that is already on the blockchain. And again, I have some errors here, so I'm not sure exactly what's wrong, but I will fix this after the session and put the fixed version on Solidity, on Canvas. So. Okay. Great. So I'll see you all